Look at this closer. The aluminum can. It seems so ordinary, so simple. It isn't. The can has a secret history, a strange beginning. The can is a necessity, a technology, an icon, and a cultural artifact, even an object of desire. And it all begins here, within the earth. Hang on tight. It's an epic journey. The can will never seem ordinary again. The perfect container, a quest for both man and nature. The nut, the fruit, and the egg. All of them excellent containers, but that doesn't mean they don't have their own limitations. But breaking, cracking, and shattering is half the container's job. An impenetrable container is useless. You have to be able to get out what you put in it. Behold, half an ounce of engineering perfection. The can. The simple can, an invention that changed civilization.
Pretty much all you need is fire and a can, and you can pretty much have any meal of the day. Put a thing of corn, pop the top off it, put it over a flame, and you just eat out of the can.
The great thing about cans is that they're accessible sculptures. They're meant to be held, they're meant to be played with, they're meant to be crushed, they're meant to be thrown away, they're meant to be saved and put on a shelf somewhere.
Cans are really one of the most highly manufactured products in existence.
It's pretty damn perfect.
So the miracle of the can continues.
The modern supermarket would not be the same without the can. The can changed our lives, the way we shopped, cooked, and ate. The can is the result of decades of relentless invention. Thousands of patents have transformed this into this. The can is as highly engineered as this, or this. Precisely designed, not a single milligram of wasted material. Efficient, cheap, and mass-produced on a mind-boggling scale. The aluminum can is among the most ubiquitous man-made products on the planet. Across the globe, we make 220 billion cans a year, 600 million cans a day, 400,000 cans every minute. That's a rate so fast that if you were to stack them end to end, they would reach the moon in under a week. And in 6 years, all the way to the sun. The perfect container. Perfect because of one thing: aluminum. Light and strong. The ideal metal. Except for this fact. In nature, there is no pure aluminum. It only exists as part of a rock. The story of the can begins here, in a bauxite mine in the wild west of the Australian outback. Aluminum is the most plentiful metal in the Earth's crust. And it is hidden within these rocks, tightly bound to oxygen, silicon, and a whole mess of other impurities. Extracting the pure shiny metal will be an epic task. The demand for bauxite is voracious. These specially designed trucks, as tall as a 2-story house, must haul and dump 104 million pounds per day. 58,000 pounds per minute, over 3 million pounds an hour, 7 days a week. a relentless onslaught of stone. But at current rates of extraction, all the bauxite deposits here will be gone in about 80 years. It took eons for these rocks to form. But in just months, modern engineering will transform them into pure aluminum, one of the most useful materials in our man-made world. Inside this steel drum, giant spikes pulverize the rock. The rock is then deep within the bowels of this giant plant. Think of this place as a gargantuan monster that feeds on bauxite and has a stomach hundreds of feet long. Deep inside the belly of the beast, digestive juices, a lethal cocktail of chemicals, break apart the rock. What remains is dried, separated, and sifted until only one final impurity remains: oxygen. This powder is now highly refined aluminum oxide. Worldwide, each year, some 320 billion pounds of rock are processed into 120 billion pounds of this fine white powder. But we are still a long way from our can. Next, our powder must make an epic journey to the other side of the planet, to a distant place where a huge amount of energy will electrocute it into metal. The making of metals was once the realm of magic and mystery. For centuries, alchemists were obsessed with transforming common materials into valuable metals. Their mystical tinkerings would eventually give way to the science of chemistry, which would one day lead to the discovery of aluminum. In 1825, chemist Hans Christian Ørsted managed to trigger a chemical reaction that produced tiny quantities of pure metallic aluminum. But purifying aluminum through chemical reactions was extremely inefficient. Aluminum remained so rare, it was as valuable as silver. But then, scientists managed to harness the power of the lightning bolt in their labs: electricity. And by the 1980s, they were testing it on nearly everything, including aluminum oxide powder.
Electricity can be used to break chemical bonds. The passage of that current results in the breakage of the bond between the aluminum and the oxygen.
The electricity tears away the oxygen molecules in the oxide powder. Left behind, pure aluminum metal. It was the birth of the aluminum age. Suddenly, aluminum ceased to be precious. At last, we could make it easily.
Aluminum is transformed into 100,000 useful things.
Today, aluminum is everywhere. On the road, in the sky, in our homes, and around our food. In fact, we produce more than almost any other metal. More than copper, silver, or gold. It is second only to iron. Today, aluminum production is a multi-billion-dollar industry. Around the globe, trains carrying aluminum oxide powder arrive daily at plants like this Alcoa factory. Here, electricity converts the powder into metal on an industrial scale. (1700 degrees Fahrenheit). Liquid aluminum. The elusive elemental metal. Something never found in nature. A man-made perfection. Pure aluminum. But there is a problem. It takes a massive amount of energy to make aluminum. The electricity needed to make the tiny half-ounce of aluminum in a single can would keep a 50-watt bulb lit for 7 hours. The energy needed to make a ton of aluminum would keep your television running for over 15 years. And to make all the aluminum in the 220 billion cans we produce each year, that would be enough to power every electrical device in Washington, D.C. for more than 34 years. Despite the colossal amount of energy, we have decided that it's worth the cost, because the can saves lives. The can was an invention that needed to happen. Food begins to decompose moments after it is harvested or slaughtered. Insects like these maggots and microscopic bacteria break down organic material until it returns where it began. Dirt. This is the cycle of life. But rotting food makes people sick, really sick. And worse, it can kill. We can thank the ruthless desires of a French emperor for solving the food preservation problem. On his endless campaigns across Europe, Napoleon's armies had to forage for food. Supplies were erratic, and soldiers often starved to death. In 1795, the French offered a cash prize to the first person who could invent a method of preserving food in a container that could easily be carried. Napoleon would have to wait some 14 years before a Parisian confectioner solved the riddle. His idea? Put food inside glass bottles, seal them with corks, and then sterilize them with heat. The heat killed microorganisms, and the seal kept disease and vermin out. But there was a major design flaw. But the very next year, an Englishman replaced the glass with metal. Problem solved. An industry was born, and food would never be the same again. Napoleon's goal was achieved. Armies no longer had to forage for food. They could carry it in cans. World War II was won on canned food. Meat preserved in 12-ounce rectangular cans sustained millions of soldiers as they fought across Europe. And the can was even going to preserve mankind. Americans were told to store canned food in their basement bomb shelters, rations for after the atomic war with the Soviets. Suddenly, it seemed as if everything was preserved in cans. Canned food was a marvel of convenience for the consumer. But filling all these cans was a laborious manual process.
Oh, no, you're right.
Meet Esther and Al Campoy, canners. Al and Esther spent 4 decades stuffing sardines into cans.
Did it smell bad?
No,
You got used to the smell. It smells like money in the bank.
Monterey, California. For a time in the 20th century, the sardine world. But here, the can nearly drove the California sardine out of existence. The little fish was no match for the onslaught of the cannery. Sardines were packed into cans faster and faster every year.
The faster you went, the faster the time went for me.
I had to keep everything going on time. And I mean, it had to be time.
And then, suddenly, the sardines all but vanished. Vanished into the can. Overfished, overcanned. The sardine fishery collapsed, and Cannery Row in Monterey became a ghost town. But there were other things to process and can. Each year, faster and more efficiently. The filling of cans had become highly mechanized. So scientists had to invent new foods that could be squished into cans automatically.
This laboratory is where new products are born and repeatedly tested.
One of the most popular inventions, spiced luncheon meat, Spam.
Mixer blades stir ground Spam meat until it becomes thoroughly blended. The raw material is then pumped to the can filling machines where the tins are automatically filled and vacuum sealed.
The can allowed vast quantities of food to be processed and preserved quickly. The food of the future had arrived. Every year, more and more cans. And to feed this perpetually increasing demand, we had to conquer engineering hurdles. Even the seemingly simple, like making aluminum thin, are epic tasks when the scale of production is so massive. Molten aluminum is poured into giant slabs, ingots, each some 45,000 pounds, 2 feet thick and 20 feet long. The blocks are so heavy, just moving them takes specially designed robotic machinery. This factory complex is the size of about 100 football fields. There is enough metal in each ingot to make more than 1 million cans. But first, it must be made thin. But how?
You roll aluminum by passing it between rollers. Think of rolling pastry, for example. The roller you use to roll pastry is hard, strong. The pastry is soft, and it will deform quite easily as you roll it.
The freshly congealed aluminum ingot is still hot. Hot aluminum is soft, softer than the cold steel of the presses. The ingot cannot be made in a single pass. It must be squeezed through the steel rollers over and over again. It is a mechanized process, machines and computers, rolling the metal thinner and thinner. Water is used to cool the massive presses and keep them from melting. The ingot is now 3,000 feet long and thinner than a poker chip, but still too thick to be made into a can. The sheet is wound so it can be moved. Each of these rolls weighs as much as 2 school buses. The rolls are attached together to form a never-ending ribbon of aluminum, rolling through the presses, becoming thinner and thinner. At last, it emerges from this labyrinth of machines at its final thickness, 1/100th of an inch, thinner than 3 sheets of paper. The roll of aluminum is now over 6 miles long and will soon be transformed into the aluminum can. Don't underestimate the can. It is a marvel of human ingenuity. The can, half an ounce of shaped aluminum. Seemingly the essence of simplicity. But don't let its looks fool you. This can only exists as the result of thousands of patents, each one improving the object slightly. This room is a library of can inventions, each card containing the design for a single improvement to the can or a can-making machine. 2,000 cards in each drawer, dozens of drawers, tens of thousands of tiny modifications.
So there's a surprising amount of sophistication in a can, so they have to be engineered and produced with very fine tolerances on the order of microns. Anything you can do to make the manufacturing process slightly more efficient, slightly faster, to reduce small amounts of the material, and the really add up in an industry like this.
Cans were once made by hand, from tin and steel. one at a time, with a soldering iron.
This man here is soldering the side seams. Say, Frank, our friend here is hollering for more canned goods. How many cans do you think we'll turn out today?
We can figure on maybe 600.
There you are. I've got 3 men soldering here. They can turn out only 600 cans a day. Pretty slow work.
Not the most efficient process, and there were other problems. The lead-soldered seals often broke, contaminating the food. But the need for speed drove innovation. We invented machines to replace people.
We've got to have cans right away.
Okay, Ed, of course we'll get cans to you. But don't worry, we'll get them there on time, too.
But building faster machines alone could not satisfy the ever-expanding demand by thirsty customers. The can had to be reinvented to break the next speed barrier. And the easiest way to produce almost anything faster is to reduce the number of parts. Cans were traditionally made from 3 pieces: the sidewall, a top, and a bottom.
Probably the greatest breakthrough that occurred was when they went to what was called a 2-piece manufacturing process. So in fact, the bottom and the sides are all made out of the same piece of material. We add an end at the top and the 2-piece container is born.
This 6-mile-long roll of aluminum is about to meet the latest in high-speed can manufacturing technology. This hungry machine feeds on sheet metal. Inside, a mouthful of pistons stamp the aluminum into shallow cups, cups that will soon become cans. From here, the cups wind their way through a serpentine of ducts until they arrive at their final destination at a machine called the ram. Here, the can is born. It happens so fast, it's impossible to see. A metal rod, called the ram, punches the aluminum cup through a series of rings. As the metal is squeezed between the ram and a ring, it stretches into the shape of the can. The sidewalls of the can are now nearly as thin as a single human hair. Engineers have pushed the technology to the limit fast metal parts can move. The ram punches out cans at a staggering rate, 33 per second.
They're producing 2,000 cans a minute on each line in the plant. That adds up to over 5 million cans a day in that plant, being produced day in, day out, 24 hours a day, 7 days a week.
Ceaseless, unrelenting. Since their introduction 5 decades ago, we have made trillions of aluminum cans. After being punched into shape and trimmed, the cans are bathed to wash away lubricant, grease, metal shards. Then, it's off to the printing press. Pigments are mixed with highly toxic solvents that will dry, cure, and bind the ink to the can. Through these hoses flow the ideas of the billion-dollar beverage advertising industry. Logo, design, color, the stuff that sells the can. Designers here at Landor, a product branding company in San Francisco, are working to make you want the can. Using text and color to create thirst and desire.
Our job as graphic designers is creating this need, this urge to ingest something simply by putting graphics on a can. My graphics, simply what I put on this can, is going to make you actually buy it.
Consumers are pretty savvy in the marketplace right now. They know when you're trying to sell them hard. And so our goal is really to get to, ideally, the subconscious and understand what they're feeling and what'll compel them to buy the product.
You walk in the store, you walk through that aisle, and your attention is grabbed by something, you walk up to it, you pick it up, you look at it. And all of those moments are a different point of contact and very important.
Getting you to pick up a product and put it in your cart is easier said than done.
Why not just write beer on a can and set it on a shelf? Well, first of all, by doing that, it has no personality. It doesn't really say anything. It doesn't really stand for anything. And that's where graphics can really help play a big part. Coors, for example, when we talk to consumers about Coors and Coors Light, the first thing that they think about is that Rocky Mountain water and the Rocky Mountains. And so you can see in their brand identity, which a lot of people call a logo, you see a very prominent of those mountains in there. And so while the mountains will reinforce the promise of a cold, refreshing type of product, it also takes them to another level emotionally in terms of when you think about the Rocky Mountains, you think of opportunities, you think of the West, you think of boundless, vast nature. Hopefully consumers will connect with that and start developing a stronger bond with the brand.
There are hundreds of brands of soda and beer, and sometimes the only substantial difference is the design on the can.
We use graphics and fonts and colors to really help create a personality and create an image for the brand. A blank can has no personality. It really says nothing, and but it's got a lot of potential to do so.
Here, back at the factory, nameless, anonymous cans are given their identity. This machine applies ink to the can so fast, the process cannot be seen with the human eye. We must slow it down to see. The inked color plates on the right roll against the cans on the left. Each engraved plate applying a perfect palette of color, 2,500 times a minute, to an endless stream of cans. This is modern manufacturing. Machines making disposable objects faster than the eye can see. An endless river of new cans. The can, a fixture of modern life. We rarely go a day without popping the top to a can. We need them. But it is not the can itself we crave, but what it contains. And most cans are made to hold only one thing. A liquid cocktail of chemicals. Soda, sweet elixir in hundreds of flavors. Designed to make us crave carbonated taste, to get us to crack open a few more cans of a sweet, bubbly concoction. But that sweetness does not come from table sugar. In fact, that's not what's inside most cans of soda. There's corn, a plant we have learned to transfigure into chemicals, industrial and edible. People have been eating and cultivating corn for over 9,000 years. Over the years, we have produced more and more corn. Our love affair with corn is based on its spectacular efficiency. These plants can grow fast and produce lots of food with very little water. Corn can do this because it has evolved a way to collect carbon. More carbon means more biomass and more calories for human consumption. The corn plant gets only 3% of its biomass from the ground, and the rest, 97%, from the air. These plants pull carbon dioxide out of the atmosphere and combine it with sunshine to spit out some 200 trillion calories a year. Corn turns sun and air into food, better than almost any other plant we have attempted to farm. Every September and October, combines set out across America's cornfields. 74 million acres in all. On that land, the U.S. grows 600 billion pounds of corn a year. And a lot of that corn is never eaten. We drink it. From fields all over the United States, trains haul corn to factories like this one in California. Corn is broken down into its molecular parts. Think of these machines as an automobile factory running in reverse, where cars come in whole and leave as parts. Deconstructed corn parts are then made into solvents, pharmaceuticals, adhesives, lubricants, and HFCS 55, high fructose corn syrup. On average, each of us consumes some 42 pounds of the stuff every year. We are hooked on HFCS 55. This highly refined sugar has become the lifeblood of the modern American diet. It has found its way into a surprisingly high percentage of everything we eat and drink, especially into processed foods. Everything from baby food to vegetables to soda pop. But transforming corn into HFCS is no easy task. It involves highly complex biochemistry. And what remains is one of the purest sugars ever engineered by man. But why go through all this effort when other sweeteners are readily available? Because HFCS is almost a penny cheaper per can of soda than actual table sugar. For soda manufacturers, that is an annual savings of hundreds of millions of dollars. Corn syrup is profit. Over 23 billion pounds of HFCS are made every year, over 2 billion gallons. That's enough to fill 70,000 tanker trucks like this one. High fructose corn syrup is shipped to rooms like this all over the world. This man is not making some complex industrial compound or conducting some mad chemical experiment. He's making soda pop. Specifically, grape soda. A potion of chemicals, artificial flavors, citric acid, sodium benzoate, red number 40, blue number 1, and HFCS 55. We drink a lot of concoctions like this every year. About 50 gallons per person. Now, soda is about to meet the can. It's going to be a high-speed crash of liquid and metal. A mechanized whirlwind of aluminum and effervescent drink. A filling plant in Worcester, Massachusetts, one of thousands located around the globe. Here, a process happens so fast that you might think you've missed it. But it's what makes the can a can. It's a highly technical and heavily engineered process known as putting the top on. The top has proven to be the biggest obstacle in constructing the perfect can. One question has plagued can engineers since the beginning.
Let me see that.
How do you design a can that has a strong seal but can be evened?
One of the key innovations has been how to open the can. And quite a bit has changed about how we open cans today.
First, the can was a perfect cylinder, sealed tight at both ends. And no matter how much we wanted what was inside, getting at it with our bare hands was nearly impossible. For most of us, anyways. But for those of us in the real world, getting into the can was a real problem. Our ancestors actually used hammers and chisels to get the job done. Until this was invented, the can opener. This might be just fine for canned food and a 1950s homemaker in her kitchen, but it wouldn't work for the beverage industry. Life on the go needed to be self-contained. They needed a can with a can opener built in.
Certainly is a new basic idea in can making.
The solution: score the top of the can and attach a ring.
What's it called, Harry?
This is the pull tab.
Good name.
For the first time, the can could be opened with ease. Trillions were made. But there were horrible, unintended consequences. People tossed the tabs on the ground. Dangerous. The problem was so severe, there was talk of banning aluminum cans. But the can was saved by one Daniel Cudzik, can engineer. In 1974, he had a revelation. The can opener is just a lever with a sharp end. What if the lever was attached directly to the can? The stay-on pop top was born. The can was now perfect. Here, at this Polar beverage plant, pop-top lids are seamed onto freshly filled cans at blazing speeds. 1,250 cans a minute. Globally, 600 million aluminum cans are filled and topped every single day. The can's epic journey is nearing its end. It races to complete its mission, to meet its final destiny in the hands of the thirsty consumer. From across the planet, the parts and pieces of the can are mined, milled, processed, painted, electrocuted, extracted, carbonated, sugared, washed, heated, wrapped, topped, and packed. And while the stuff to make the can and its contents travels thousands of miles, the filled can itself often doesn't travel very far at all. These American brand sodas, purchased at a cafeteria in a factory in Vietnam, were not made in America. They were made at a filling plant in Vietnam. Many canned beverages are filled locally. The Coca-Cola Company alone uses over 800 filling plants in more than 200 countries around the globe. The reason? Water is heavy. Soda is mostly water, and heavy things are expensive to ship. So, manufacturers ship just a concentrated syrup to local filling plants, where they are mixed with filtered water and carbonated. Filled cans are then packed on trucks for delivery, and the can itself, while strong, is not infallible. The modern can is so thin and so light, it can fail under the stresses of long-distance travel. This machine replicates the stresses on a six-pack in a truck. But the can is designed perfectly to do its job. Contains soda from plant to consumer. But for some, the survival of the can is paramount above all else. Old cans. Cans tossed into the woods decades ago. Stuart Crook is a member of a small subculture, the can collector.
Pre-World War II, probably like 1938. Acme was one of the biggest brewing prior to World War II. They had plants in San Francisco and in Los Angeles. Oh, it's wonderful. This moment of discovery. It's a continuation of the story, basically. The story started when it was manufactured, then it was sold, and then it was bought, then it was consumed, and then it was disposed of. And then they thought that was the end of the story, but it wasn't. The story then continued 40, 60, 80 years later when somebody with a device called a metal detector came along, discovered it, removed it from the ground and restored it and put it back on the shelf, and now it lives on as a collectible.
Not many of us hold rusty old cans in high regard, but for those of us like Stu, they're a coveted prize. Here in a motel in the Santa Cruz Mountains, south of San Francisco, an organization is meeting, a chapter of the Brewery Collectors Club of America.
Yeah, like this can here. This guy's been digging for 30 years, and this is the first time they ever found him was this year.
And it's a local can too.
Yeah, it's a local. Oh, yeah.
Pretty cool.
They sold this in our area. What do you want to trade for that?
This truly goes to show that one man's trash is another man's treasure.
That one there is $60. Good deal.
Yeah, a year or so ago on eBay, I'm like, oh wow, you can buy like actual cone, a real live cone top, and so I started kind of getting into it again. So I only have probably 20 or so. And this is the first show I've ever been to.
Colorful. I mean,
figure out exactly where people are finding these cans and or what's the best way to go about building a collection.
This would be considered about a grade 2 minus, 3 plus dumper, where this would be considered about a grade 4. This is what they call a tall profile, where these are lower and they actually have ridges.
I'm hoping to find a London Tavern Ale cone top. That's one that I've wanted for my collection for a long time.
Cans worth hundreds or thousands or even tens of thousands of dollars.
I don't like the rust at all. As you can see, I have nice clean cans.
Well, it doesn't have the name of any brewery right on the front label. It just has beer, and it has a propeller on the front of a plane, and so everybody calls these the propeller cans. I found probably 200 of them.
Not every can is valuable, but all the same, the can and its evolution are a brilliant trophy of extraordinary engineering. The modern can. Form and function in perfect harmony. But can designers are still pushing the limits of can technology. The can of the future may do things you never thought possible. Here at the Crown Company near Chicago, the next generation of can is being invented. This is the Research and Development Lab. Because of the massive number of cans we produce each year, the slightest modifications to its design can have enormous consequences. One of the biggest ongoing challenges for can engineers is how to reduce the amount of metal in a can. This early can weighs more than 4 times as much as each of these modern cans.
If you remember back to these cans, these older cans, they were literally pure cylinders. And over time, the industry found ways to slowly reduce the diameter of the top of the can. That, of course, reduces the diameter of the end and can save some significant material.
The process is called necking. The top of the can is bent inward until the diameter is shrunk by about ½ an inch. A necked can uses 20% less aluminum than a can. It might not seem like an earth-shattering invention, but because of the large scale of production, this single innovation saves can manufacturers millions of dollars. But there is something even more important for all of us. Consider this. It takes the energy of about 3/4 of a cup of gasoline to make the tiny amount of aluminum in a single can. Necking all the aluminum cans we make each year keeps some 2 billion pounds of toxins out of the atmosphere. But making the can more efficient will only take you so far. The answer to reducing the can's environmental cost is right in front of us. In the metal itself. There is something special about aluminum. It's immortal. Aluminum is a pure element, a primary building block of matter. It can be recycled in, melted, formed, melted again, forever. And the most astounding thing is that the energy needed to make a recycled can is only 5% of that needed to make a virgin can. United States, half of all cans are recycled. In as little as 9 weeks after the can is tossed in the recycling bin, it's back on the supermarket shelf. We recycle 1.6 billion pounds of aluminum cans every year. That's more than 3,500 times the weight of the Statue of Liberty. More than 50 billion cans. Recycling saves a colossal amount of energy because you only have to melt the aluminum, not make it. That is such a tremendous savings that if we recycled every can we use each year, it would save enough energy to power 1.3 million American homes for a full 12 months. The making of cans. Almost 7,000 new cans every second. It continues night and day across the globe. An unquenchable desire for aluminum, for the can and what it contains.